Hi all, this is uh, recording 6, class 6 for Math 2621 probability for application class. Today we are going to discuss a geometric distribution. So before starting geometric distribution, I would like to recall what we did last time. In last time we discussed random variable and probability mass function. So if x is a random variable, then we learned two methods to express probability mass function of x. So one method is listing the output or the outcome of the random variable and corresponding probability in a table like this. Or we can use piecewise function form to denote the probability mass function like this: P1, 2, P3, P1 when x equal x1, x equal x2, and so on. So these are the basic or the general method we can denote a probability mass function for any random variable which has a finite outcomes, finite possible values here. So this should be finite. Okay. So now today we are going to learn some specific random variable which is still a discrete random variable. So here this is a random variable discrete. So we are still discussing about the discrete random variable. So today we are going to discuss specific discrete random variable which has brand name distributions. So the first distribution we are going to learn is geometric distribution. So before understand what is the process of geometric distribution, we need to learn binary trials. So there are some experiment we can do where we have only two outcomes, like tossing a coin or a game, winning or loss, or a true-false question, or a question with yes/no answers, or an experiment with success and failure. So those are some example with binary or the two possible outcomes. Okay, so those are also known as binary trials. So the binary means two. So according to the context, we can define one of this output or the outcome as a success, and other one will be the failure. So if you are interested with tossing, when you are tossing a coin, if you are interested with getting head, so then the probability of getting head is our success, and probability of getting failure is our probability of getting tail is our failure. Okay, this should be tail. Okay, so suppose we are doing this one independent and identically binary. So that means we are going to do this one several times, but each time this is independent to each other. And the probability of getting success is P. Okay, so that means if we are tossing a coin and our interest is getting head, probability of getting head is going to be our probability P. Okay, and this can be any value P, any probability value between 0 and 1. Okay, so if there's a, now let's define a random variable called x for this process for binary trials. So we are repeatedly doing this process until we get the success. Okay, until we get the success, we repeatedly do this process. Okay, so for example, when you are tossing a coin, suppose our interest is to get head. So then the if we got head in first trial, so x will take 1. If I get head in second trial, so that's mean I get tail in the first trial, so that's mean this is 2. And if I get head in third trial, so that's mean first success. Okay, so success is getting head. Okay, and probability of success is the probability of getting head. Okay, so we can repeatedly do this one. So in this case, you can see your x is going to be countably infinite. So that means it's discrete random variable. Okay, so the geometric distribution is talking about when your random variable take countable infinitely many values, discrete values. Okay, so if if you define your x in this particular way, so then we can say, we can prove x follows a geometric distribution denoted by this notation, and this sign means approximately follows. It can say follows geometric distribution, and this is the parameter. So parameter p, and you should memorize this equation, or you can bring this one into a cheat note. This is important. So this is the equation to find the probability of a known value x when x follows a geometric distribution. This p is the probability of success. And when I'm asked you to write down the probability mass function of geometry, you should specify the possible values for x. Okay, so don't skip that one. So this says when you see the first outcome, probability of getting first success. Okay, probability of getting first success when you are repeatedly doing a binary trial. Okay, so let's do a quick example to understand how we can use this equation, geometric distribution equation. So this example says a product produced by a machine has 4% defective rate. Let S see the number of items inspect until the first defective occurs. Okay, so in this case, if you have a defect, if you have a product, it can be either defect or no defect. And then here in this case, probability of success. So we are interested in getting defect. Okay, so that's mean here the same as probability of defect is 0.04. So this is the parameter value for the probability mass function of geometric distribution. So here x is the number of items inspected until the first defect is occurred. So in this case, x follows a normal distribution. X follows a geometric distribution with parameter 0.04. We can write down the probability mass function as 1 minus 0.04 to the power x minus 1, 0.04. And here x goes 1, 2, 3 to the infinity. Okay, so that's how you can write down the probability mass function of x, because x follows a geometric distribution. Part B question asks, what is the probability that the first defect occur at the third item in spec? So in here question asks, what is the probability of getting x equal 3? So here you have to plug x for 3, which is 3 minus 1, and here 0.04, and find this probability. 1 minus 0.04. Okay, so in Cal, I got this value. Zero point 0.036864. Okay, so please round your answer to the 4 decimals. So go 1, 2, 3, 4 decimals and check the 5th decimal. And if it is greater than or equals to 5, then round up the fourth decimal. Okay, so here 3639. This is the probability of getting x exactly equal to 3. So that means this is the probability of getting first defective at the third item inspected. Okay, so one more question. This is part C. What is the probability that the first defective occur in the first 3 inspection? So that's mean you will get the defective in first place, defective in second case, okay, or defective in third item. Okay. So that's mean in this case x equal 1, here 2, here 3. So the question asks to find the probability of x less than or equal 3. So that's means same as finding probability of at x equal 1 plus probability of x equal 2 plus probability of x equal 3. So here 1 minus 0.04, 1 minus 1, 0.04, plus 1 minus 0.04, 2 minus 1, 0.04, plus 1 minus 0.04, plus 1 minus 0.04, 3 minus 1, 0.04. So use your calculator and find this answer. Okay, so please practice to use your calculator as well. So here you will get 0.04 plus 0.0384 plus 0.0369, 0.1153. Okay, so that's the final answer for 4 decimal places. Okay, so hopefully that makes sense how to use geometric distribution to find probabilities related with geometric distribution random variable. Okay, so if you have any questions, please visit me, my office hours tomorrow from 9 to 12 p.m. That's mean tomorrow is Thursday. Okay, I mean Tuesday from 9 to 12 p.m. If you have any question, please feel free to visit me. Okay, now I'm going to do another example. After this example, we are done with discussing this topic. And in the next video, it will be a little longer, but I will mention more about the next video after this example. Okay, so in this example, it is asking in a baseball event, first team to win 3 games win the championship. Suppose there are only 2 teams and each team has same chance to win any of the game. What is the probability distribution of the number of games? Okay, so here let's define n is the number of game. And suppose these two teams are A and B. Okay, A and B, and I'm going to define N is the number of games to win the championship. Okay, so the question here is, can we use geometric distribution? Okay, so let's check whether can we use or not. Okay, so the first point, each game is independently playing, that's of course. Okay, and each game is a binary trial, either win or loss. So it's either win or loss. Now let's see what are the possible values for N. What are the possible values for N? Okay, so let's decide, or let's calculate the possible values for N. Okay, so let's see what are the possible values for N. Let's write down the omega. Okay, so we can play 3 games. So then either A win or B win, all 3. So A win means B plus, B win means A loss. Okay, so these are the one possibility of playing 3 games. Okay, so in this case, N equal 3. We are playing only 3 games. Now let's see if we play 4 games. Let's see what are the possibilities when you are playing 4 games. So when you are playing 4 games, A can win. This cannot be happen. Okay? So this cannot be happen because when A wins 3 games at once, so then we don't want to play 4 games. So this is not going to be an outcome. So it will be this one for team A perspective. For team A, and these are the team B. Okay, so this is for team A possibilities when you are playing 4 games, and this is for team B. Okay, so this case we are playing 4 games. Okay, so one more case. I think it is 5 games. So when you are playing 5 games, okay, so we cannot have this one. Okay, so we cannot have this one because if we if A win 3 games at once, they will win the championship, and we don't want to play 2 more games. Okay, so that means be careful when you are writing the possibilities. So we can have this one. Okay. So this is for team A. And these are for team B. Team B, we have the similar items, B, B, A, B, B, A, B, A, B, A, B. Okay, so these are the possibilities for B when we are playing for this set n equal 5. So let's see, we can have 6 games. Okay. So A, E, B, B. No, we cannot have 6 games like this. If I have like this, still no. Okay, so let's, so that's mean n equal 6 is not possible. So that's mean the possible values for n is only 3, 4, 5. Possible values for n is 3, 4, and 5. This is not a infinite, countable infinite set, so that's why we cannot use. So this implies we cannot use geometric distribution. Because if you want to use geometric distribution, possible values for x must be goes from x to here should be goes from 1 to infinity. Okay, so but here the possible values for n is because we define our variable as n is going only take three values. Okay, so that's the reason we cannot use geometric distribution. Now let's find out the probability distribution of number of games. Okay, so we have to find the probability of n equal 3. So n equal 3 will take on only 2 cases. So that is probability of A plus probability of B, B. So since these are independent games, we can break it A plus B. So this means half plus half. So you will see, if you simplify this one, this will be 1 over 8 plus 1 over 8, which is 1/4. Okay, so now let's see what is the probability of n equal 4. So when in n equal 4, we have these outcomes. So we have to find the probability of each of these, which is probability of A, B, A plus probability of A, B, A plus probability of B, A. So these are under winning A plus probability of B, A, probability of B, A, plus probability of B, A, B. So this will be, one of this will be half to the power 1, 2, 3, 4 times 1, 2, 3, 4, 5, 6 times 6. So you will get 6 over 60, which is 3 over 8. Okay, so now let's find n equal 5. Probability of n equal 5. So here you have to find the probability of each of these items. So here 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So you will get 12 of 1/2 to the power 5, which is 12, 1 over 32. So it is 3 over 8. Okay, so now I can write down the probability mass function of n. So n takes 3, 4, and 5, and probability of n, which is 1/4, 3, 8, and 3, 8. So this is the probability mass function of n. So this is method 1. And method 2 is use the piecewise function. Method 2. Okay, so method 2, we can use the piecewise function form. Probability of n equal little n. That is 1/4, 3, 8, and 3, 8. This is n equal 3. This is n equal 4, and this is n equal 5. This is the second method. So you can use either method. I show you the both methods, but you can pick either one and show the results. Okay, so that's all for this video. This is little shorter video, but it's very important to understand these concepts and how to use geometric distribution to solve a question, and how not to use, when not to use the geometric distribution. Okay, so it is not always you can use a geometric distribution. There are some situations you can use geometric distribution and some situation you cannot. So please check whether these things are matched when you are using geometric distribution. Specifically check whether the possible values are infinitely many. If possible values are finite, definitely you cannot use geometric distribution. So that means you can use the methods what we learned in last class. So you can use a table or piecewise function to denote the probability distribution when n is finite, but when n is infinite, one for now, it's definitely going to be a geometric distribution. And we will learn more probability mass functions, the brand name probability mass functions later. So this is a one method, and we will learn more on chapter 2. Okay, so that's the end of this video, and I will do mean and variance of a probability mass function and mean and variance of a random variable in next video. So see you on video 7.